All right, so just a few words on why are we doing this workshop. So we had some discussions before organizing this, and it seems clear that biomedical researchers and graduate students across our different centers and departments come from a wide variety of training backgrounds, and that not everyone has had an opportunity to spend as much time as they might have liked on statistics beyond maybe an introductory course in undergraduate programs. And it is also true that our research publications rely heavily on statistics, including hypothesis testing, and it can be very difficult to interpret your results or publish your work without the right stats. There are course offerings at UBC that attempt to get people familiar with stats and R, but often these presume a working knowledge of R already or have an incredibly steep learning curve. So I think there's still a niche for informal sessions like what we're putting on today. So our plan for this afternoon is to do a little bit of an introduction to Rstudio. So everyone's familiar with that interface. We did choose Rstudio because it's primarily what the course offerings at UBC use. Keegan will lead us through the materials that he's prepared on hypothesis testing and doing t-tests in R. We're hoping this will take about 50 minutes, and we'll do that all together as a large group. And then after we move through that material, we'd like to divide up into some breakout rooms. We have material prepared for bootstrap distributions and permutation testing, as well as ANOVA and multiple comparisons. And we'll leave it up to you at that time to decide which of these topics you want to explore during the workshop. But all of the materials are available on GitHub. So our hope is that if you choose one or the other, you'll be able to do the other one as a self-guided tutorial. And then at the end, we have a survey link that we're hoping you would respond to. Mainly, we'd like to know what kind of topics you might like to see in a future workshop along these lines. So we're hoping that after this session, we'll have some increased familiarity with our Rstudio, that you'll be comfortable performing the t-tests that Keegan is going to go into, and assessing the null hypothesis for your statistical tests based on the observed statistic you're getting from your sample and understanding its p-value. For the second part, we're hoping that we'll get into the relationship between the bootstrap distribution and the sampling distribution, as well as how the randomization and the permutation test produces a way of doing stats tests on your data. From the ANOVA side, we're hoping to get into multiple comparisons and describe the multiple comparison problem and some methods that can be used to control the types of errors that are inherent in these kind of stats tests. So that's the link for this wrap-up survey that I'll post later on in the meeting. But at this point, I will stop my screen share and turn it over to Keegan to start getting into the material.
All right. Hello, everyone. Jeff has already introduced me, but to say it again, my name is Keegan Flanagan. I'm going to be going over the intro to R, the t-tests, and also the bootstrapping section. Now, this is going to involve a lot of work with the material that I have asked everyone to download from GitHub, but I imagine some people probably didn't get around to it. So we're actually going to start just by doing that. So in the chat, I just put a link to that page for anyone who hasn't done it yet. And what you're going to do is you're going to bring up the GitHub page just like this, going to click on code, then you're going to go to download zip, click on it. I'm not going to because I already have it downloaded. And then that should download it to somewhere on your computer. Just put it somewhere you know you can find it. Then I'm going to ask all of you to open up Rstudio. Then once it is loaded up, please go to File, Open File, find wherever you have stored it on your computer, go into the Stats Workshop folder that you'll download from GitHub, go to Introduction, and click on Intro to R, and Open. I'm just going to give a couple seconds just for everyone to make sure they get that done. And while we're waiting, I'd like to mention that if anyone has any questions, please feel free to put your hand up or just unmute yourself, shout something out and interrupt me. We're going to be going pretty fast, so make sure you make yourself heard. All right, I'm going to hope that everyone has this open now, and we're going to launch right into it. Let me just say welcome to our studio.
Excuse me?
Oh, yes?
Sorry, I'm not able to open it because I clicked on Intro to R, but it said I need to get a software to open it, so I'm guessing I missed that step because I have a Windows, I don't have a Mac.
Okay, so you click, so you actually so do you have RStudio then?
I downloaded RStudio. I've got an R64-bit. Is that what it's going to be? Because I downloaded R.
Mm-hmm.
And I've got, I think it says RGUI 64-bit. And then I tried to open this.
I think maybe we'll hop over to a breakout room and try to get you going with an RStudio. Does that sound okay?
Yeah, that does. Thank you.
Okay, we'll let Keegan continue, and I'll create the breakout room and try to help you with that while he's going on with the intro. Thanks.
Okay, thank you so much.
All right. Now, before I continue, is anyone else struggling with getting this brought up? I mean, if you are, I would suggest you head on over to the same breakout room. It sometimes takes a while to figure out these things with RStudio, so it's best that we just keep going other than that. Now, where was I? Oh, yes. So welcome to RStudio, everyone. RStudio is a great place for organizing your work in R and also integrating other programs into your workflow. Everything I do in R is always done in RStudio, and I imagine you will do the same. So let's take a moment to get familiar with the layout of RStudio. So you'll probably notice that there are 4 different windows in R. This first window, the one you are reading right now, is the scripting section. This allows you to edit and save R scripts that you can then run right inside of RStudio. It also has this little tab bar at the top that allows you to switch between different scripts and data sets, sort of like in a search engine. Then in the lower left window here, this is the console section. So this section is what's actually running R. You can type stuff right into it, like 2 + 2, enter, you get 4. And this is essentially all it does. Most of the time, we're going to be running things in scripts rather than running things in the console, but it's a good way to sort of see what R is doing. Then there is, in this upper right-hand corner, we have the environment section. This is going to show you all the different things you have saved into R, such as variables and data frames. More on that later. And then finally, in this lower right-hand section, there are several useful tabs. You can look at the different files you have open. You can look at different packages that you have installed and loaded. And most importantly, you can look at help files, which again, we will talk more about later. So moving on, let's get into what is this file we're actually looking at. This is called an R Markdown file, but what is that? So this is a special kind of script that is very powerful for integrating R code into documents and websites. But for now, I'm just using it because it's a very convenient scripting format for running these kinds of tutorials. So everything you've been reading up to this point is part of the Markdown section of the R Markdown file. Now we're actually going to create a coding section. We're going to create a block of code using 3 grave accents, which should be right underneath your escape key, and then squiggly brackets R. So I've already done that for you. And now everything in this gray box can be run by R. So if you want to put any notes into this, we need to actually put a little hashtag mark here. That will make this whole line green, and then everything in this line will be ignored by R. So it's not going to try to understand what you have in your notes. Now let's actually make something we can run now, and run it by hitting this green arrow at the top. So just hit it, and bam, 2 + 2 = 4. So hitting the green arrow at the top of the block will run everything in the block, but we need to figure out how to run the stuff line by line. So we can run just one line of code by hitting Command + Return if you're on a Mac, or Control + Enter for Windows. If you're working along with this right now, I would like you to select line 3 that has 3 + 6 on it, and try to run just that line using the command. So I'll just do mine, and we get 9. Okay, so that was all good, but let's actually try doing something interesting in R now. I'm just going to clear my screen. That's better. All right, so defining variables. Whenever we calculate or create something in R, we can save what we made as a variable to be used later. We do this by specifying a variable name and then saying is equal to basically anything we make. For example, x = 2 + 2. Now you can see in the environment, I've got a little thing called x, which is equal to 4. We have saved the output of 2 + 2 in a variable, and now we can print that variable using print bracket x, and we get 4. Now, but what was this? What is this print plus brackets kind of thing? Well, this is a function. Functions are used for doing all of the interesting stuff in R, the stuff more interesting than basic addition and other simple math. So let's look at some of the functions that are built right into R that can do special tasks. We can use the C function to create a vector of different objects. For those of you who aren't familiar with vectors, they're basically just kind of like a list of things. So now up here, x is equal to the numbers 3, 6, 2, and 7. Then we can get R to calculate the mean of our vector, or we can have it calculate the standard deviation of our vector. And you can probably already see that even though we're doing simple stuff still, we're already saving time with R. But now let's get into what is the most important function in R, which is the help function. This can be used to get information on any of the other functions in R. So we're just going to try running help for the mean. And we can see now that a little help thing has popped up in this lower right-hand square that goes over the arithmetic mean. And looking through this, even for something simple like mean, there's quite a lot of information here. But the most important parts are the usage and argument sections. Usage is going to show you what it should look like when you're typing it into a script. And then it will also show you the order and defaults of all of the values. Sorry, the order and default of all of the arguments. Then the section below explains to you what those arguments actually are. It gives you their name. It tells you what kind of thing can be used as an input. For example, for trim, it always has to be some decimal between 0 and 0.5. And it tells you what it's supposed to do, what the argument is used for. Well, for example, na.rm tells us whether or not we're going to ignore non-applicable NA values. So now is probably a good time to explore the different ways that you can specify argument inputs. So we're going to create another vector real quick, call it x again. This time it's going to be longer and it's going to include an NA value. So what if we want to calculate the mean of this vector while trimming off 10% of the observations and removing the NA value? We can either put all of the inputs directly into the function in order. So for this one, you can see we've specified x as our object. For trim, we've set it to 0.1, and for na.rm, we've set it to true. So we can run that, and we get 4.66. Now, there's another way we can specify these arguments, and this is what I actually recommend for anyone who still feels that they're a beginner, which is that we specify the values we want for each argument using their name in any order that we like. So here we actually say x equals x, na.rm equals true, trim equals 0.1. Doing it this way makes it a lot easier to keep track of everything. Once you get to functions with like 10 or 20 arguments. All right, so all of those functions we just covered, those are great, but R's real strength is in its open source packages. There is already an R package for basically every problem you can imagine. If there's not, someone will invent it pretty soon. And all you need to do is figure out what that package is called and how it works. There are a couple of steps to using a package that are universal. We're going to go through some of these using the boot package, which some of you will use later, but we won't actually do too much with it yet. So you'd have to click install.packages boot. I'm going to skip this because I've already got it installed. And then you select library boot. This is what actually loads it in to whatever area you're working on. So you have to do this every single time. Another important note is that the help function also works with functions from packages. You can see here we've brought up the bootstrapping table. So we've got the description, the usage, the arguments, many of them, then the details. And as you can probably tell, this help file is really complicated. And that's because help files contain completely extremely technical explanations that would show you how you can do anything with the function. And it takes a lot of practice to figure out how to extract the important information that you actually need for whatever analysis you're doing. For this tutorial, we're going to try and guide you to the right parts of the help files, just to help you out a little. Now, moving on to data frames. Data frames are the main way in which R stores data. We will not use them too much today, but it is important that you learn how to use them just a little bit. So here's a super basic data frame we're going to create. We're just going to name it data. Then we're going to take a look at it with view. This opens up a new tab. We can see we have Sam and Mike. Sam's really tall. Mike is somewhat less tall. Going back to the Intro to R tab, then we can select one column using the format data frame, money sign, column name. So we can look at just the heights. And then we can select a row using data frame, square brackets, row number, comma. So now we can look at just what's going on with Sam. Okay, the last thing I'm going to mention is plotting. R has some pretty good plotting software built into it, so we're just going to be using that base plotting software for today. Let's quickly make a couple of vectors. We're going to call them X and Y. Now we're going to make a histogram using X as an input. And we've got a histogram right here with the frequency of each number showing up. Then we're going to make a scatter plot using X and Y as the X and Y coordinates using plot. There's what that looks like. And then finally, we can also use things from our data frames as inputs for plotting programs. So let's use our data frame to make a bar plot. We're going to make height be the sort of inputs to the bar plot, and then we're going to have the data frame names as the names for each bar. And there we go. We have the height of Sam and Mike. So just one final note on doing stuff in R before we jump straight over into doing the t-tests is that there are many different ways to do things in R. Sometimes one way is more efficient or better than other ways, but it is often the case where multiple different solutions are equally good. So if you're doing something in this workshop that is a little different from how I do it in the answer sheet, you should not worry about it too much as long as your answer still makes sense. All right, and with that, we are going to head on over to the t-test section. I'm just going to stop sharing for a second as I set this up. All right, so now that we know the very basics of working in R, let's learn about hypothesis testing and t-tests so that we can learn how to implement them in R. We're going to be jumping back and forth between the slides in Rstudio, so just make sure you have them both on hand. Okay, so before we continue, there are a few important definitions that I want to make sure is clear to everyone. So first, population. A population is all of the individual units of interests. So this is every person on Earth. This is every lab mouse in existence. This is what we want to know about, and 90% of the time it is entirely impossible to measure. We aren't going to go out and measure every human being on Earth, so instead we have to take a sample, which is a subset of the population that is small enough that we can actually observe it. This is what we're actually going to conduct our statistics on, while hoping that it is an accurate representation of the population. Now, then there are two kinds of descriptive statistics I want to go over. First, there are descriptive statistics, and these are things that describe the data. They're things like the mean, the median, and the standard deviation. And the inferential statistics. These are things that allow us to understand something about the data or understand something from the data. One example would be the p-value. I am going to refer to both of these things interchangeably as statistics as we're going on. So it's important to understand that statistics can mean a couple different things. All right, now let's move on to hypothesis testing. In the realm of statistics, there is always a null hypothesis, designated HO, and an alternative hypothesis, designated HA. The null hypothesis is usually something boring, like these things are the same, or the treatment has no effect. While the alternative hypothesis is something more interesting, like, oh, our treatment does improve something or have an effect on something. So our goal is to find evidence to reject the null hypothesis in favor of the alternative hypothesis. Now note that we collect evidence to see if we can or cannot reject the null hypothesis. We never accept the null or the alternative hypotheses. This way of speaking is important, that it's always rejecting the null and never accepting anything. Another note is that the null and alternative hypotheses should be decided before you start the experiment, not after you've collected your data and looked at it. All right, so this method of hypothesis testing naturally leads to two different kinds of possible error. Either you will reject the null hypothesis, even though in reality it is true. This is called the type 1 error. Or you can decide you cannot reject the null hypothesis when it is in fact false. This is called a type 2 error. Understanding these two types of error is very important. They're going to come up a lot through the rest of this workshop when we're talking about error rates and power. So if anyone is confused, please speak up now. No? Okay, going to move on then. So in order to actually test our hypothesis, we need statistics. We need to know how likely it is that we would see our results we get from our samples, if the null hypothesis was true, so we can decide if it was reasonable to reject it or not. Now, the scientific body has decided that there needs to be less than a 5% chance that your results are different from the null due to random chance. This is the infamous p must be less than 0.05 that every reviewer wants to see on your papers. Now, how do we actually use statistics to figure out if p is less than 0.05, and what is p and what is the importance of 0.05 in the first place? Well, before we get to that, we need to understand some distributions. Now, the population distribution is fairly intuitive. It is a distribution of all the different values of a variable in a population. It is also effectively impossible to know in most situations. We like to talk about it a lot in statistics because it helps people understand the fundamentals of what's going on, but we will pretty much never actually see one in the field. So instead of using the population to do statistics, we use the sampling distribution. This is a bit less intuitive. This is the distribution of all the different sample statistic values you could theoretically get when you randomly draw a sample from a population. And unlike the population distribution, there are many different ways to estimate or make an educated guess about the sampling distribution. Now, I imagine some of you might be still a little confused about the sampling distribution. So we are going to jump into R and actually looking at an example of one. So I'm going to ask you to once again go into that stats workshop folder. I'm going to ask you to go into the t-test work subfolder and then open up the t-test script working RMD file with Rstudio. Right, and I'll see you all there in just 1 second.
Hi, is there an easy way to clear the console?
Clear the console?
Yeah. Or do people not do that in R?
I mean, I generally don't, since the script is more important. So it actually, I don't remember it off the top of my head.
You can click the little broom to clear all the data and save variables.
Cool. Thank you.
Yes, no, but that's the saved variables, and that is different from the console.
Oh, no, there's another broom in the console.
Oh, okay, there we go. Okay,
thanks.
Sorry. All right, sounds good. So if everyone hopefully has this brought up, I'm going to launch into it. So sampling distributions. So we are going to create a super basic normal distribution to represent our sampling distribution. The code for that has already been done for you right here. And now after you create this, I'm going to ask you to try and draw some samples from this sampling distribution using the rnorm command. So I'm going to give you a few minutes now, just 3 minutes or so, to draw these samples and create a little histogram of them. And if anyone has any questions or gets stuck, please let me know.
Can I get some help, please? Like, I'm not sure how I'm supposed to get those values, like what I'm supposed to click.
So now we're actually going to be typing something in. So the first step is looking through the instructions. You would type in help rnorm.
Yeah, that's already written in here.
Yeah, so then you'd be looking through this. And all right, so you're wondering how to get the arguments then?
Yes, like everything's already typed in. It's just I'm wondering how to get the histogram that you said we had to get.
Okay, yeah. So after you've created the sample, you're just going to type in sample hist, so to create a histogram of that sample.
Okay, but then it also says breaks equal 30, xlab equals histogram of samples.
Ah, sorry. Oh, I must have. Okay, so you probably have opened up the t-test script RMD file.
Yes.
That is the file that has all of the answers on it.
Okay.
Yeah, so I'm sorry that this is very confusing. Everyone, please open up the t-test script working RMD file.
Oh, okay.
If anyone has gotten mixed up with that.
Okay. Right, so then I go to sample.
All right, so the time is just about up. So I'm sorry if anyone is still working, but as I just clumsily explained, there is a script with all the answers in it. So if you're ever really having trouble understanding something, I'll ask that you can please look over there. But now we're going to actually take a look at this histogram and sampling distribution that we have created. So if you look at this histogram, you can probably notice that most of the samples that you took are all centered around this mean value. They're all centered around 10. And that should make a lot of sense, because looking at this sampling distribution, the highest probability density is right around 10. So whenever we draw a sample, it's most likely that it's going to be somewhere in this sort of central region of values. And in fact, we can actually draw a little thing here, and we can say that 95% of the time, any sample that we draw is going to be somewhere in this region. So let's say somewhere between around 6 and 14. Now here is where the hypothesis testing comes in. So what we can do is we can say that if the null hypothesis is true, we expect our sampling distribution to look just like this. So this is going to be our sampling distribution underneath the null hypothesis. Then let's say that we extract a sample from some kind of treatment group of ours, and we calculate a statistic from it, and the statistic ends up being right here. It ends up being, say, around 16. Well, now we can say that if the null hypothesis were true, there is less than a 5% chance that we would find a value this large for our sample statistic. So then what we can say is that, okay, it's so unlikely that we would find a sample that is this extreme if the null were true, that we conclude that the null is false and we reject the null hypothesis in favor of the alternative hypothesis. This is the fundamental idea behind all hypothesis testing. We are seeing how likely it is that we got our sample if the null is true. Does anyone have any questions about this point or about what I just said? All right, I'm going to keep moving then. Clear these drawings. All right, so this shape is probably familiar to all of you. It's the normal distribution, and it's going to come up a lot. Now I want to take a second to describe to everyone why it comes up so often. So I'm going to head back to the slides now. Portion of the screen. All right. So the reason that it comes up so often is because of something called the central limit theorem. Now, the central limit theorem states that the sampling distribution of a sample mean is approximately normal for large sample sizes. So what this means is that I can have an extremely non-normal population distribution. So this is mortality from the Spanish flu, and we can see that there's a big spike at infancy and then these two kind of bumps here. It's very not normal. But then if I take a sample of 30 individuals from this population, and then I calculate the mean age of death, and I store that into a histogram, then I repeat that 10,000 times, each time putting the mean into this histogram to create a sampling distribution, I create something that is roughly normal shaped. Now, this is not very intuitive, and I suspect that some of you are confused. For now, I just want you to accept that this is true. Now, I'll suggest some resources at the end of these slides for people who might want to understand this better, but you just need to understand that whenever your sample size is large enough, you can assume relative normality of the sampling distribution. Okay, now we are going to move on to the student's t-statistic. There are a variety of statistics that can be used to calculate the probability of getting a certain sample value. We will be looking at one of the most popular, which is the student's t-statistic. Excuse me. The student's t-statistic is used to calculate the probability of getting a sample mean under a normal curve. In this simplest version of the t-statistic, that normal curve is defined by the null hypothesis. So looking at this equation, there's two things I really want you to take away from this. The first is that the numerator is the sample mean minus the mean under the null hypothesis. So that means the t-statistic is a measure of the difference in means. The second thing I want you to observe is that the denominator is the standard error, which means that the t-statistic is also dependent upon the sample size we are using. And with that, we're going to jump back over into our working script again. All right. So now we're going to look at the t-statistic and the t-distribution. So I want you to quickly just run this code as is. Just hit this button up here quickly. And let's switch over to this version. And you should get something that looks just like this. Now this is the sampling distribution for the t-statistic, assuming the null hypothesis is true. And we're going to call it the t-distribution. Now looking at this for a couple seconds, it should begin to make sense. Our null hypothesis is going to be that there is no difference between the mean and the sample mean. And that means that the distribution is going to be focused around 0. It's most likely that we won't see any difference between the sample mean and the mean under the null. Now what I want you to do is I just want you to copy this whole section right here into this and run the section again. Now what should happen is that you're going to get a little red region. Now this is what we call the rejection region. So in this little section, everything to the right of this line and below the curve, that is exactly equal to 5% probability. So if we get a t-statistic that is anywhere in this region, we can say that p is less than 0.05, and we can say that there is a significant difference between the means. Now, what we just did is sort of like a manual version of conducting a t-test, where you take the distribution, you find the area that is equal to 5%, and you see where your t-statistic falls into it. But R also has a whole bunch of built-in machinery that makes doing t-tests much simpler. So now we're going to actually do a t-test, just using that framework. So let's say the test we are trying to accomplish is to see if the data is consistent with a population mean of 10. This is going to be our null hypothesis, that the mean equals 10. Now, what's our alternative hypothesis going to be? Well, let's say that the alternative is that the mean is greater than 10. This means we will be looking for our test statistic in a region which is to the right side of the distribution. So that's just like what we did up here. We're going to be looking for a value that is to the right. So we will need to set the greater than option later down the line as we're running this. So this next little block of code, the one sample t-test, I'd like you to all try and do it yourselves. You're just going to work through it, and if you get stuck anywhere, please ask me a question, and I'll do my best to help you. All right, I'm going to set the timer for, let's say, 8 minutes.
Sarah, can I ask a question real quick?
Yeah, absolutely.
How come the plots, the histograms, they don't show up they keep showing like in the console or the terminal, but not at the bottom where we normally would see a plot?
Yeah, that's just how R Markdown usually works. It shows up there rather than in the plotting area. Mm-hmm. It is a little bit inconvenient in some ways when trying to scroll back and forth between things. I will admit that, though, as Jeff suggested, you can copy paste things directly into the console and they should show up in the plotting region.
Oh, it just only shows up in the console. It doesn't go into a plotting region still.
Yeah, it just shows up in the script for R Markdown. That's just kind of how it's supposed to work.
So then, but if you wanted to, like after you're done and then save these, because like with the plots, it's just easy, just go file, save. How would you save it? Is there a different method then you'd have to use to save it, pull it out from here?
I'm not sure. I think usually with R Markdown, you would actually have this set up so that you could turn this whole thing into like a website page or something. So usually it's not really made to do that. You would kind of keep them as part of a whole thing you created, which is why there's not like a thing set up to do that easily.
Okay. All right. Thank you.
Yeah. Sorry about that. I know it can be inconvenient.
Yeah, it just kind of blocks, like jumps everything down. You have to scroll, but it's fine. Okay, thanks.
If I can butt in, there are two different things you can do. If you're just kind of sharing the image, you don't really care about the quality. You can actually just usually right click or command click on Macs. the image in the R marking document and copy it there. If you want to tweak it, what you can do is you can take the code that makes the plot and then paste it directly into the console, and then use the plot window like Jeff suggested.
Okay, thanks everyone.
No problem.
Alrighty, time is just about up now, so I think we're going to keep moving along. I hope everyone is finished, but I'm very sorry if anyone is still working. All right, so now we're going to do a little just for fun section where we're going to analyze our type 1 error. So this time around, it's going to be pretty easy for us to estimate our type 1 error because we already know what the mean above we set it to 10. So we know that our null hypothesis is true for our sample. So what we're going to do is we're going to generate 20,000 samples using n-iter, which we're going to call n-iter. Then we're going to create a place to store all of our type 1 errors called hout, and we're going to set our alpha value, our significance level, to 0.05. Then what this chunk of code here is doing is it's just going to run that thing we just did up here 20,000 times, and each time it incorrectly finds that the p-value is less than alpha, it's going to add 1 to hout. So after we're done with that, and we're going to divide hout by the total number of tests we do. We're going to see what number pops up. Oh, let me just. Should take a minute. All right, and we get 0.0533. And you'll probably notice that this number is very similar to our alpha value. And that is how it works. The alpha value is what sets the type 1 error. It's how we control how much type 1 error we are willing to let ourselves have. This is going to be really important when we move on to multiple comparisons. So if you're planning on going into that, keep this in mind. That's all for now. So we're going to move back into the slides. All right, so I want to have a quick side note about the difference between one-tail and two-tailed tests. So one-tail and two-tail are referring to the rejection region. A one-tailed test tells you if your sample is either greater than or less than what we would expect under the null hypothesis. It investigates one or the other, not both. A two-tailed test tells you if your sample is more extreme than we would expect under the null hypothesis. So it investigates both greater than and less than. Now, deciding between these two is entirely a function of how you are wording your alternative hypothesis. Is your alternative hypothesis that the sample mean is greater than the null? One-tailed greater. If it's less than the null, one-tailed less. If it's more extreme than the null, so it doesn't matter which side, then two-tailed. And now note that how you word your alternative hypothesis should be based on what results you are interested in. Do you only care if your sample is greater than the mean under the null? Or would it matter to you if it was just more extreme, if it perhaps had the opposite effect of what you are expecting? These are things that we need to decide while we are designing our null and alternative hypotheses. So now there are actually 3 different variations of the t-test that everyone should know about. The one sample t-test is basically what we just went over, where we compare a sample mean to the mean under the null hypothesis. Now the 2 sample t-test is a little different. It is used to test if 2 independent populations are significantly different from each other, where the null is always that there is no difference between the populations. This is the bread and butter of statistics. This is my treatment group different from my control group? You've probably all encountered it at some point, and you probably all will need to do it at some point. Now, the paired t-test is another very useful kind of test. Well, it's used to test if a population undergoes a significant change after a certain treatment. So this is the situation where you have some individuals and you measure them, and then you perhaps give them a treatment like a drug, and you see if they have changed over time. This is your did the patient improve after they were provided with our drug test. Now let's jump over into R and go into some examples of how you can actually do these different tests. All right, so this is the section where I'm just going to kind of give you a bit of time to go over these at your own pace. So all of this code here, the two-sample t-test and the paired t-test down here, I just want you to kind of try and work through these, reading all of the instructions and try and answer as best you can. I think we can give ourselves around 15-ish minutes to do this. All right, so if you have any questions, again, just let me know, and good luck. All right, so one last thing I want to cover for t-tests is that when doing any statistical test, the statistical test always has some assumptions. If these assumptions are not met, you cannot do the tests. For the t-tests, they all have fairly similar assumptions. They all assume that the sample we took was randomly sampled from the population, and they all assume that the variable is normally distributed in the population, though it is robust to this assumption if the sample size is very large. This is due again to the central limit theorem, where as long as the sample size is large, we can assume normality. The two-sample t-test has one extra assumption, which is that the standard deviation of the variable is the same in both populations. So if you have your two sample groups and you look at them, and for one of them, the data points are really all clumped together and they're all similar, and for the other one, it's totally, completely spread out, then that's a problem, and you won't be able to use the normal version of the two-sample t-test, although we did cover a version that does not assume equal variances in the R code as well. Now, t-tests are great, but they cannot do everything. So what do we do if our sample statistic is not normally distributed, or our sample size is small? And what if we want to look at a statistic other than the mean, because the t-test works specifically with means? Well, in these situations, we need bootstrapping and permutation testing. So if you're interested in knowing how to deal with these situations, I would suggest that you go to that breakout room later. Now, another problem is that what if we have more than two groups we need to compare? What if we have multiple treatment groups instead of just two? Well, then we need ANOVA and multiple comparisons. So if you really want to know how to deal with this situation, I suggest you jump over to that breakout group later. So then the last thing I want to say is just a couple of additional resources. The Analysis of Biological Data by Whitlock and Schlutler is a fantastic textbook that covers all of this in much more detail. It's the only textbook I ever opened up after the class was actually done. I highly recommend it. And then also there is an introductory R tutorial that is made by the Brain Circuits Research Cluster. There is a link in the PDF slides that you all should have downloaded from the GitHub page, and it will go into a lot more detail on how to do stuff in R if that's where you're really getting stuck. Now with that, I'm going to stop sharing, and me and Jeff will work on setting up the breakout rooms.